Hi, everyone. Let's continue on chapter 10, part 2. In the first part, we talk about the basic theories of acid and bases, what they are, and also we talk about the reactions between an acid and base. If you have a hydroxide base, the products will be water and a salt. And today, we'll keep continuing chapter 10 and talking more about how do we quantify and define the acidity or basicity of a solution, and also how do we determine or how do we put a scale on determining the acidity of a solution. And in the end, we're going to talk about more about salts, this particular type of ionic compound. Now, in order to talk about the acidity or introducing the pH scale, first we have to talk about a very important phenomenon that happens in water, okay, even in pure water, that is self-ionization of water molecules. Okay, this equation shows that even in pure water, there's a very extremely small percentage of water molecules that will transfer protons from one to another. Okay, like showing this equation, one water molecule will transfer a proton to another to end up with a hydronium ion and a hydroxide ion. Of course, they're in equal amount. Okay, but like I said, even in pure water, this process happens, but happens in extremely small percentage. How small? Here I put a scale here, is 1 over 10 million. So basically 1 over 10 to the 7th. That small percentage. That means over in every 10 million water molecules, only one water molecule happened, in this case, the self-ionization. But it does happen that produce equal amount of hydronium ion and hydroxide ions, even in pure water. Okay, and then because of that, because the amount of hydronium ion and also hydroxide ions are equal, so the whole water, okay, this compound is still considered neutral. Okay, still considered neutral, but it does happen. Now, what's more important about is this process of self-ionization of water not only happened in water, but also happened in any solutions that contains water as the solvent. And because this is an equilibrium, we can actually write the equilibrium constant, K equals to, of course, product over reactant. The over reactants are water, pure, so that's not including the equilibrium constant. So basically, the equilibrium constant is basically K equals to hydronium ion concentration times hydroxide ion concentration, because you got two ions, and again, the reactants is water, so we didn't include the water in the expression of equilibrium constant. So the concentration of these two multiplied to each other, like I said, the chances is 1 over 10 million. So you multiply these two concentration, you get 1 times 10 to the negative 14th, because 1 over 10 to the 7th times 1 over 10 to the 7th, you get 1 times 10 to the negative 14th. And that is the equilibrium constant for self-ionization of water at room temperature, okay, around 24 to 25 degrees Celsius. It is temperature dependent, but at room temperature, the equilibrium constant of this process is 1 times 10 to the negative 14th. And we call this constant ion product constant for water, Kw. W starts in water. And now, like I said, this equilibrium constant, okay, because it is a constant, that means it doesn't not only apply for pure water, it applies to any solution, despite the contents of the solution, as long as water is the solvent. So that means as long as you have a solution, water is the solvent, you always have this mathematical equation. The concentration of the proton or hydronium ion times the concentration of the hydroxide ion equal to 1 times 10 to the negative 14th. And that tells us for the concentration of these two, as long as you know one of them, you can use the concentration, you can use the constant to calculate the other, because those two are inversely proportional. Okay, such as these two derived equations. If you know the hydroxide equation, you can use Kw divided by hydroxide equation, hydroxide concentration to get the proton concentration. Or if you know the proton concentration, you can use Kw divided by the proton concentration to get the hydroxide concentration. They are inversely proportional, just like A times B equal to a constant. So that means as long as you know A or B, you can use that constant to calculate the other, B or A. That's the beauty of this ion product of water, the equilibrium constant. So after you know that, we can discuss the acidity or the basicity of a solution, or how do we determine whether a solution is acidic or basic. So like we said earlier, in water, because each water, when the self-ionization happens, the transfer of electrons from one water to another, you end up with equal amount of proton and hydroxide ion. So that means when proton and hydroxide ions are equal and they're multiplied to each other equal to 10 to negative 14th, that means when they're equal, the concentration of each should equal to 10 to negative 7th. So if that's the case, if you have a solution with equal amount of proton concentration, or again, hydronium hydro concentration, equal to the hydroxide concentration. And of course, when they're equal, their concentration are both 1 times 0 times 10 to negative 7th. If that's the case, we call the solution neutral. Of course, water is also a neutral compound, but doesn't matter it is water or a solution contains some content such as sodium hydroxide, a sodium chloride solution. As long as the concentration of the proton and the hydroxide ions are equal, and again, when they're equal, they both must equal to 10 to negative 7th, because the ion product constant is 1 times 10 to negative 14th. If that's the case, we call the solution neutral. Now, if you add some proton concentration or add some compound that can generate proton, what will happen is if you add hydronium ion or proton into the solution, then you will find out the proton concentration will be higher than the hydroxide concentration, because again, you add proton, or again, if your compound generates or gives proton in a solution, then the proton concentration will be higher. Now, when the proton concentration is higher, the other one, hydroxide ion concentration, will be lower. Remember, they're inversely proportional. So you have this mathematical equation. If one is higher, proton concentration is higher, it will be higher than 10 to negative 7th. And the other one must be lower than 10 to negative 7th, because again, the ion product water, when they multiply each other, must be equal to 10 to negative 14th. So when proton concentration is higher than 10 to negative 7th, it must higher than the hydroxide concentration. We call the solution acidic. Okay, acidic. So now you know that when you have acidic solution, it doesn't mean you only have hydroxide proton. You have both. The only thing we classify a solution acidic is because proton concentration is higher than hydroxide concentration. Now, very similarly, instead of adding proton, if you add some hydroxide ion or a compound that can release hydroxide ion, then your hydroxide ion concentration will be higher than the proton. And when the hydroxide concentration is higher, it must be higher than 10 to negative 7th, and proton will be lower than 10 to negative 7th. If that's the case, we call the solution basic solution. Okay, basic solution. Again, in a basic solution, you do have both species, but hydroxide concentration will be higher than proton concentration. So that's the whole mathematical like a relationship between a solution that is neutral, acidic, or basic, which is also summarized in table 10.4 of your book. Again, when proton concentration equal to hydroxide concentration and they're both 1 times 0 times 10 to negative 7th, we call the solution neutral, including water. Okay, when proton concentration is higher, it must be higher than 10 to negative 7th, then we call the solution acidic. When the hydroxide concentration is higher, it must be higher than 10 to negative 7th, we call the solution basic. But keep in mind, no matter your solution is neutral, basic, or acidic, you have both species present in that solution. The difference is the relative content of each compared to each other. Okay, so here are two very basic calculations to show, to test you, or to confirm you if you understand that topic. They ask you if you're given either hydroxide concentration or proton concentration, can you calculate the other, and also meanwhile determine if the solution is neutral, acidic, or basic. Let's take a look. The first equation gives us hydroxide concentration, which is 10 to negative fourth. We know 10 to negative fourth is what? Is greater than 10 to negative 7 because it's negative. So hydroxide concentration 10 to negative fourth is greater than 10 to negative seventh. Okay, greater than 10 to negative seventh. That means hydroxide concentration will be higher than proton concentration. If that's the case, our solution is basic. Already, we know that it's basic. Okay, now next, we know that the proton concentration multiply the hydroxide concentration will equal to 10 to negative 14th. So you use 10 to negative 14th divided by the hydroxide concentration, you will get the proton concentration, which is 10 to negative 10th. Again, ion product of water Kw divided by the hydroxide concentration, which is 10 to negative 4th, you get 10 to negative 10th, 1 times 0 times 10 to negative 10th, which is the proton concentration. Okay, so the second example, tells us the proton concentration is 2.0 molar. 2 is a large number, so definitely greater than 10 to negative 7th. If that's the case, we know proton concentration will be greater than hydroxide concentration. That means the solution is acidic. Okay, acidic, we term that. And then the proton concentration multiply the hydroxide concentration equal to the ion product water, which is 1 times 0 times 10 to negative 14th. Then I use the ion product water divided by the proton concentration, I get the hydroxide concentration, which is 5.0 times 10 to negative 15 molar, which is very small because your proton concentration is very high. So in this case, proton concentration is much, much, much higher than the hydroxide concentration for this acidic solution. Okay, again, make sure you practice these questions. When you are given a concentration of either one of these two, you should be able to calculate the other. And also by looking at the concentration of either one, you should be able to tell whether a concentration, whether this solution is acidic or a basic or neutral using these two slides or these notes or for the mathematical relationships. Okay, now next. Once we know the concentration of a proton or hydroxide, you notice that they're mostly in exponent because the concentration mostly in our encounter solution, the concentration of these solution of protons concentration or hydroxide will not be very high. So most times you are dealing with a scientific notation of exponent. So to make things more convenient, we invented, or a chemist invented, a scale. Okay, by taking negative log of the proton concentration. Okay, again, proton concentration normally is 10 to negative something, negative exponent as a scientific notation, which is a relatively small number, which is sometimes more difficult to present or to get a more visual and fast determination of the acidity or basicity. So we take a negative log of the proton concentration and we call this calculation, we call this answer of negative log of proton concentration the pH, okay, pH value, okay, pH value. After you taking a negative log of the proton concentration, most likely the pH will be a number of a whole number, some point something followed by a fraction, like a 4 point, like these pH scales showing here, like 2.2, 2.8, 7.2, 8.5 will be a much more straightforward number, so that we can by looking at it with like a reflex to tell what is the acidity or basicity of a solution, or even more straightforward, whether the solution is basic or acidic, because we're taking negative log of the proton concentration. It is a much more compact way to represent the acidity. Now, because the ion product water is 10 to negative 14th, okay, so pH range by taking the minus log of the proton concentration will normally be between 0 and 14. There are pHs higher than 14 or lower than 0, but usually the solution we encounter daily will be having a pH of in the range of 0 to 14 when the solution is at or around room temperature. Okay, like I said, you can take a look at the pH scale now. If we use pH as an indicator, you will find out our daily encounter solution, like our daily life solutions, like lemon juice, vinegar, milk, and seawater, and milk and magnesia, and household bleach. You can see they have a very visual, like compact pH values. Some are smaller number, less than 7. Some are greater number, greater than 7, but they're between the range of 0 and 14. Okay, now let's take a look. How do we know, how do we understand the pH? Okay, pH. Because pH takes the log of, negative log of proton concentration. Okay, negative log of proton concentration. That means when the proton concentration is higher, okay, the negative log is going to be lower because you're taking the negative log. Remember, where proton concentration higher, the exponent is less negative, right? Negative 4, negative 5, negative 3. Next negative means the pH scale, negative log, will be lower. So in another word, when you have a proton concentration higher than 10 to negative 7th, which is acidic, then your pH will be lower than 7 because 10 to negative 7 minus log will be 7. So when you have a neutral solution, okay, neutral solution, 10 to negative 7, then negative log of 10 to negative 7 will be 7. So neutral pH is right at 7. Now, if your acidic solution, the proton concentration is higher than 10 to negative 7th, then your pH value will be lower than 7. Okay, lower than 7. So in another word, acidic solution will have a pH of lower than 7. Basic solution will have a pH higher than 7. Of course, neutral solution pH is right at 7. Okay, this is the scale comparison showing you that. You can see that when you have acidic solution, the high proton concentration is greater than 10 to the negative 7th. And then the hydroxide concentration will be smaller than 10 to the negative 7th. But we're only talking about negative log of proton concentration. So the pH will be lower than 7. Okay, very similar when you have a basic solution. Okay, the proton concentration will be smaller than 10 to the negative 7 because hydroxide is higher. So proton concentration is smaller than 10 to the negative 7. The pH is actually higher because the exponent is more negative. Okay, again, always refer to the scale to know the relationship between proton concentration versus pH. Okay, versus pH. But if proton concentration is between 10 to negative 0 to 10 to negative 14, our pH again is between 0 and 14, but they're opposite. Higher proton concentration, lower pH. Okay, lower pH. Now, in our lab, there are two ways of representing or measuring pH. One way is actually contained in your lab kit. Okay, your lab kit is using a strip called pH paper or pH strip. You can actually estimate the pH of a solution, but it's very rough because you probably only can tell the pH between in the scale of 1, 2, and 3, and 4, and without much fraction. Sometimes if it's a color between two whole numbers, you may do it in half. But again, it is a rough way of estimating a pH of a solution between 0 and 14. Of course, I know in your lab kit, you may have some indicators. Okay, your indicator may actually also tell whether a solution is acidic or basic in a more straightforward way. But if you want to know the pH of a solution, you have to use a pH paper in your lab kit. Now, in our lab, there's a more accurate way of measuring pH, which we can actually get the accurate pH value, which is using this device called a pH meter. Okay, it has a glass bead probe you can insert into a solution, and the machine will tell you of course, the accurate reading of the pH in 2 decimals, okay, 2 decimals. Of course, the machine is dependent on temperature as well. And also, in order to use a pH meter, most likely or most times you have to use a solution, buffer solution, 2 solutions to calibrate the machine before using it to measure your pH. Okay, these are a way of measuring the pH scales. Again, that's just the most compact way and also most useful way of determining whether a solution is basic or solution, or how acidic or basic a solution is. Okay, now these 2 exercises are further testing your understanding about the concept of proton concentration, pH, acidity, basicity of a solution. Let's take a close look, or again, kind of like review what we studied. Okay, the first question is asking, hey, I have a solution with a proton concentration of 1 times 0 times 10 to negative 4th. Okay, again, when you look at this number, you know this is a number greater than 10 to negative 7. And when proton concentration is greater than 10 to negative 7, we know the solution is acidic. You can actually write down already this solution because the proton concentration, oops, okay, let's do it again. The proton concentration is greater than 10 to negative 7th, so the solution is acidic. Okay, solution is acidic. Now, of course, the question asks us to calculate the pH. We know pH is very straightforward of negative log of proton concentration. Okay, the proton concentration is given, so negative log of 1 times 0 times 10 to negative 14th. Make sure you put a parenthesis in your proton concentration when you do the calculation in your calculator. Of course, this can be done even without a calculator. The pH value will be 4 because it is a 1 times 0 times 10 to negative 4th. So the pH 4 also tells us it is acidic solution because the pH value is lower than 7. Okay, that's the first question, very straightforward. Now, the second question gives us hydroxide concentration instead of proton concentration. But again, when you look at the value, you know the hydroxide concentration is greater than 10 to negative 7th. So that means hydroxide concentration is higher, proton is lower. So this solution is basic. Okay, this solution is basic for sure. Now, next we calculate the pH. We know pH is negative log of proton concentration. But here we're not given the proton concentration. We're given the hydroxide concentration. So our first step before calculating the pH is to calculate the proton concentration. Again, we use proton concentration equals to the ion product water divided by the hydroxide concentration. Remember, these 2 multiplied together equals to ion product water. So I use Kw divided by hydroxide concentration, I can get proton concentration. So 1 times 0 times 10 to negative 14th divided by 0.04, I get this proton concentration. Okay, get the proton concentration. Then I plug in negative log of proton concentration, again, for the parenthesis of the proton concentration in your calculator, I get a pH of 12.6, which is greater than 7, which confirmed of our determination that it is a basic solution. Okay, again, this summarizes you how do we calculate the pH. When you're given proton concentration, you can use that equation directly straight. pH equals to negative log of proton concentration. But if you were given hydroxide concentration, you cannot use that to calculate pH directly. You have to convert the hydroxide concentration to proton concentration using the ion product water, and then use negative log of proton concentration to calculate the pH. Okay, next, I will leave this up to you. I think is another practice very similar, telling you the hydronium high concentration means the proton concentration, and ask you to calculate the pH and determine whether it's acidic or basic, and also meanwhile calculate the hydroxide ion concentration as well. So this is kind of an overview of what we have learned so far. I hope you use it as a practice. I think I have the key in the note area to for you to confirm your answer. And also, of course, you can always ask me. Okay, and next quick one. Okay, next quick one is we know pH is negative log. Okay, negative log. Oh, as a matter of fact, I have that. Okay, let me write it since I'm started writing already. Of proton concentration. Okay, relative log concentration. So if we know the proton concentration, I can calculate the pH for sure, no problem. But sometimes if you were given the pH instead, and ask you to calculate the proton concentration, like I do it backwards, how do we do that? Okay, this is basically simply math and algebra conversion. When you have something pH is equal to negative log of proton concentration actually equal to 10 powered by negative pH. Okay, basically you move the negative sign to the pH, and then because the log is the base number 10 log, so it is 10 powered by minus pH will be the proton concentration. So this is again mathematical equation converting the expression of pH backwards. Proton concentration will equal to 10 to the negative power of pH. Okay, pH. So if like this case, when we have a pH of 5.85, we know it's acidic, right? 5.7. Then they ask you the proton concentration, basically proton concentration equals to 10 to negative 5.85. Okay, 10 to the negative pH scale. Okay, of course, you have to convert that in your calculator to a scientific notation. 10 powered by negative 5.85 in your calculator equal to 1.4 times 10 to negative 6. Again, I'm sorry, negative 6 should be an exponent. Okay, let me change that. Okay, this one should be an exponent. Okay, and that's it. Okay, that's the how do we calculate the proton concentration based on pH in 10 to the negative pH equal to proton concentration. But again, you have to convert it into scientific notation in your calculator. Okay. Now, like I said, after we talk about the acidity or basicity of a solution, our final task for this chapter is to discuss more property of a salt, to give you more info about salts. Okay, this unique type of compound. Like I said, salt is an ionic compound. The ionic compound. Salt actually comes from the reaction between an acid and a base. So that means when you have a salt formula, you can actually tell, okay, you can actually tell which part is from the acid, which one from the base, because again, salt is from an acid-base neutralization reaction. Between the exchange of the ions after you're getting water, the other product will be the salt. So again, the salt is actually a compound derived from an acid and base reaction. So when you have a salt, the positive ion, because it is ionic compound, the positive ion will be from the base. Okay, will be from the base. The negative ion, okay, like this one, Cl minus, will be from the acid. Okay, will be from an acid. So that means you can actually write the formula of the acid and base where the salt came from based on the formula of the salt itself. Because sodium is from the base, the positive ion. So we add OH for the sodium, we get the base structure, NaOH. And chlorine is from the acid, so we add H to the chlorine, we get the acid, hydrochloric acid. Okay, hydrochloric acid. So again, looking at the salt, you actually can tell what base and acid this salt is derived from. Okay, again, another example shown here, KCN. Like I said, this is the salt. The K, the positive ion, is from the base. So we add OH to the K, we get KOH, which is the base where the salt is from. And also CN, which is the negative ion, Cn minus, which is from an acid. So we add H to the Cn, we get HCN. Okay, so we get the acid and base where the salt is coming from. Okay, I put red here. Pairing the negative ion with H to get the acid, pair the positive ion with OH minus to get the base, so that you get the parent base and acid for any particular salt. Okay, you may wonder why do we that? What's the use of this concept? Why do we need to figure out what acid and base the salt came from? Because with that knowledge, we can actually tell whether a salt, when dissolved in water, the solution is basic, neutral, or acidic. Because some salt, okay, some salt when dissolved in water, they may change the pH of water. They may make the pH more acidic or more basic, or remain neutral for water. So knowing the parent acid or base can help us to give a very straightforward way of determining the pH or the acidity/basicity of a salt solution. Okay, here's how do we decide. When a salt is from a strong acid and a strong base, the solution of the salt will be neutral. Okay, here's somebody wondering, what is strong acid, what's strong base? If you are confusion with that, please pause the video, go back to or go back to the chapter of part 1 of this chapter 10. We talk about the strength of acid and base. We have some strong acids, most of the acids are weak acid. We have some strong bases and some weak bases. So based on that topic, you actually can tell whether you have an acid or base, whether it is strong or weak. Again, in part 1, we discussed the strength of acid and base. Okay, here coming back, when you have a salt that came from a strong acid and a strong base, then the salt solution will be neutral. The examples are these two, sodium chloride and potassium bromide. The reason is sodium hydroxide is a strong base, HCl is a strong acid, potassium hydroxide is a strong base, HBr is a strong acid. So both parents are strong, the salt is neutral. Now, if you have a salt that came from a strong acid but a weak base, okay, strong acid but a weak base, if that's the case, then the solution of the salt will be acidic, okay, because you can see the parent acid is stronger, so the solution will be acidic. Okay, the examples are these two ammonium salts. Okay, ammonium salts, the most straightforward examples are ammonium salts, which are acidic because ammonium ion came from the weak base, ammonia. Okay, we talk about that's the property only weak base you see this chapter. Okay, ammonium is a weak base, so ammonium salt is from ammonia, okay, which is a weak base. And of course, these two examples, no matter hydrochloric acid or nitric acid, these are strong acid. So ammonium salts like these two are strong acid, weak base salt. Then the solution of these two will be acidic. Okay, on the other hand, if you have a salt with a strong base but weak acid, okay, like these two, okay, sodium hydroxide, potassium hydroxide are both strong base, but the acid part, like this is acetic acid or a carbonic acid, these two acids are weak acids. If that's the case, the base part is stronger, so the salt will be basic when dissolved in water. You have a basic solution. Of course, last part of this table, if you have a salt coming from a weak acid and a weak salt, so both parties are weak, then it will depend on the strength of the acid and base. We won't discuss much for the purpose of this class, this fundamental class. But if you have a salt with weak and acid and weak base, it will again depends on the relative strength of the weak acid and weak base, and will come more calculations. So we don't discuss that in this purpose, but you have to determine the first three types: a salt from a strong acid, a strong base, a strong base of a weak acid, or strong weak base and weak acid, or strong acid and weak base salt. These three types, you have to know whether a solution is a basic or acidic. Of course, the challenging part is, can you figure out the parent acid or base? Okay, here this table shows you a few examples. Okay, some salts are from weak acid, strong base, or weak base, strong acid, or strong acid, strong base, or weak acid, weak base. You can take a look at them and see if you can determine by yourself. You can cover the pH, cover the category, and see if you can determine them. For example, okay, this ammonium salt, okay, is from a weak base, a strong acid, because nitric acid is strong, ammonia is weak, so the solution will be acidic. Okay, you can see the pH is 5.1, it's acidic. Okay, another example is here to sodium salt. Okay, we know sodium is a strong base, and sodium chloride, the acid is also strong, so the pH is neutral. But hydrogen fluoride, HF, hydrofluoric acid, is a weak acid, so NaF is a strong base, weak acid salt. You can see that it's basic because the base is stronger. Again, these are examples of the salts with their pH with the category and see if you can understand, and most importantly, determine the acidity or basicity of these salts. But again, if you come with the salt that has weak acid or weak base category, okay, we don't discuss much in this class. It's not in the scope of this purpose of this class. Okay, here are some practice. Okay, I want to go over one or two with you, and then you take a look at the others and see if you understand. Okay, let's take a look at the first one. Okay, taking the first one. Strontium chloride. Okay, like I said, the positive ions, strontium, came from the base. So you add OH to the strontium, you get the base, strontium hydroxide. Okay, strontium, the charge is 2. Okay, it's group 2 element. And the negative ion is chlorine. So you add a hydrogen to the H minus, you get HCl, which is a strong acid. Okay, strontium hydroxide is a strong base, HCl is a strong acid. So strontium chloride is a salt with strong and strong. So the salt is neutral. Okay, salt is neutral. Okay, again, this is how we decide. Let's take a look at the second one. Again, I'll leave the other two for you to practice. Okay, the second one, aluminum bromide. Okay, aluminum Al came from the base. So we write the formula, aluminum hydroxide, which is the base. And if you guys review the strength of the base, you know aluminum hydroxide is a weak base. Aluminum hydroxide doesn't actually dissolve in water. It's a weak base. But the acid HBr is a strong acid. So we have a weak base, strong acid solution. So the solution will be acidic. Okay, solution will be acidic. Okay, because the acid is stronger. Again, I leave the bottom two for you to consider and see if you can determine the parent acid and bases, and also determine whether the solution of the salt is acidic, basic, or neutral. Okay, and next, also related to salt is a concept for buffer. When we talk about acid, base, and salts, we have to discuss this unique type of solution called a buffer. A buffer is a solution, a very unique prepared solution. And this solution has a unique property that is to prevent the major change of pH when small amount of acid or base is added to it. Okay, you have a solution that is, again, purposely prepared, but this solution contains some contents that will prevent the change of pH when you add externally some acid or base to it. Usually, if you add acid or base to water, the pH is going to change dramatically. But if you have a buffer solution, when you add acid or base to it, the pH change is going to be minimal. Okay, here is the picture showing you what the function of a buffer is. What is a buffer? You can see that if you have pure water, okay, let's say pure water, no matter you add acid or base, you can see the pH is going to change dramatically. If you add water, if you add acid, okay, add acid, the pH is going to decrease fast. If you add base, the pH is going to increase fast, okay, from 7. Okay, that's what happens when you have pure water. However, if you have a buffer, okay, you can see that no matter if you add acid or base, the pH change is very minimal. Okay, the line is almost horizontal, but again, there's still a change. It's not really horizontal. Still, if you add base, okay, if you add base, the pH is still going to increase a little bit. If you add acid, the pH is still going to decrease a little bit. So you can see that the line is a little bit tilted, but not very much. But again, that means when you have a buffer, the change of the pH is very minimal when you add acid or base, but it's still going to be changed. Okay, there's the pH won't be constant even you have a buffer. The buffer cannot hold the pH constant, but it will minimize the change. Okay, make the change very minimal, but still at acid the change is going to decrease, at base the change is going to increase. But you can see that compared to the change of water pH, the buffer pH change is very flat, okay, very minimal. That is the function of buffer. Now, what is a buffer? Okay, a buffer is basically a combination of two species, a weak acid and its conjugate base. Okay, that's normally the combination of buffer. We do have some weak base and conjugate acid, but most commonly seen buffer is a combination of a weak acid. Okay, we know weak acid, we use the formula HA as to represent, like a generic formula HA to represent. Then the conjugate base of it will be taking a proton away to get A minus. Okay, this is a buffer system. the weak acid Ha and A minus, which is again the conjugate base of it. You add them together, prepare in an equal amount. Actually, you get a good buffer. Okay, for example, this is a carbonic acid, okay, H2CO3, which is a very weak acid. And you take a proton away, you get a bicarbonate ion, which is the conjugate base of the carbonic acid. So if you have a solution containing both species, then the solution will be serving as a buffer. Okay, very basic. Now, how does this work? Okay, how does it work? In a very straightforward way, the buffer works in these two following equations. That is, if you add base, okay, if you add a base, the acid, the weak acid is going to react with the base to convert it to what? To the conjugate base of the acid. So basically, the externally added base is consumed by what? By the acid, because your buffer solution contains a weak acid. Now, if you add acid to it instead of a base, then the acid is going to be consumed by the conjugate base of the acid, okay, the A minus. So you both have the acid and base part in the buffer solution. It can consume either the externally added base or acid. The acid will consume the base added. The base, the conjugate base, will consume the acid added to convert them between back and forth. You can see that if you add base, the acid is converted to conjugate base. If you add acid, the base is converted to the conjugate acid. So you always have these two species present. Okay, the amount will not be equal. Initially, if they're equal, if you add base, then the acid will be decreased, the base will be more. If you add acid, the base will be decreased, the acid will be more. But you always have a combination of these two species because you're converting between these two species by either acid or base. But bottom line is, no matter you add acid or base, they will be consumed by the components of the buffer, either the weak acid or the conjugate base. And if that's the case, the change of the pH will be minimum because the added acid or base will be consumed. Okay, this doesn't work if you have a strong acid because the conjugate base of the strong acid is not basic enough. Okay, it has to be weak acid and its conjugate base. Okay, weak acid and its conjugate base. Okay, here this chart shows you buffer system is very universal across our daily life, is also in our research lab, and more importantly in our biological system. Our blood, okay, blood is a liquid blood, is actually a very good buffer system. It contains a lot of buffering system, not just one system, a lot of buffering system. Some are from ionic compounds, or some are from proteins, organic products, and which can maintain our pH of our blood in the range of 7.35 and 7.45. Okay, higher or lower than that pH range will be lethal, will be extremely dangerous to our biological system, to our lives. So our blood pH has to be maintained at that very narrow range. That is the contribution of all types of buffer systems in our biological system, in our physiological system. Okay, and finally, okay, last topic of this class, we're going to talk about something also related to acid and base and salts, that is electrolytes. Okay, electrolytes. Now, the definition of this electrolytes, this word, came from this very famous experiment. That is, you get an external power, you have a light bulb, and then you connect the electric circuit using a solution containing some compounds, containing some acid or base or salt compound, or some even none of these two, three. But you have some solute in a solution. So to complete the electric circuit, and you have two electrodes inserted, you can see that. Now, the experiment basically wanted to know if the solution of a compound conducts electricity or not. If the compound does not conduct electricity, okay, like ethanol, like sugar, like this, your light bulb will not light up. And we call these compounds non-electrolyte, okay, non-electrolyte. But if your compound conducts electricity, you see the light bulb get very bright light up. We call those compounds strong electrolytes. And of course, if your light bulb is like a very dim, very small, like a minorly lighted up, and we call those compounds weak electrolyte, means they still conduct electricity, but it's very weak. We call them weak electrolytes. So that's the basic definition of electrolytes, how they're first defined. But nowadays, we know why some compounds that conduct electricity, some compounds dissolving don't conduct electricity. We have a newer definition. But first of all, we want to explain the experiment. Why some compounds conduct electricity? Because those compounds, when dissolved in water, will either ionize or dissociate to give free ions. Okay, we have learned a lot of free ions in this chapter, right? Ionic compound, acid or base, they will all generate free ions. Hydroxide ion, protons, they're all free ions. If a compound can generate free ions, then that compound will conduct electricity in water. If a compound like sugar, ethanol does not dissociate or ionize to generate free ions, then they will not conduct electricity. Then the light bulb will be off, will not be lighted up. Okay, those are the basics principles behind this. And because we know why some compounds conduct electricity, why some weakly conduct electricity, why some don't, we have newer definition of electrolytes. Okay, electrolytes, especially strong electrolytes, are chemicals in aqueous solution completely dissociate into ions, or almost completely dissociate into ions, or ionize into ions. If that's the case, they are a good conductor of electricity, and we call them strong electrolytes. Okay, not because we know the reason why they conduct electricity. Now we have a better definition of electrolytes. Okay, strong electrolytes are the ones that, when dissolved in water, completely or almost completely ionize or dissociate in solution. That means they completely give free ions, and those are called strong electrolytes. Not now based on whether your light bulb is brighter or less brighter, based on the chemistry behind it. Now, what type of compounds are the ones that completely dissociate or ionize? The ones we study in this chapter are strong acids, strong bases, and soluble salts. Okay, we know soluble salts, they're definitely completely dissociate. Strong acids, strong bases, when we study the strength of them, we learned strong, the word means what? They completely ionize or dissociate. And because of that, strong acid, strong bases, and soluble salts, they will completely dissociate or ionize into free ions. And because of that, they are very good conductors. We call them strong electrolytes. So these definitions are based on the chemistry behind it, no longer based on experiment, whether your light bulb is brighter or dimmer. Of course, weak electrolytes, if you want to know, are the ones that partially ionize or dissociate. You don't have a lot of free ions, unlike these are completely free, partially ionized, and those are called weak electrolytes. Again, we're based on chemistry. Okay, that is all for chapter 10, and I hope you know all these. Again, we have a lot of tiny individual concepts, and I hope you understand again the chemistry behind it. And you can always go back and forth for these two videos, and hope you grasp all the concepts and also be able to calculate, especially define acidic, basic, or neutral solutions. That is all for chapter 10, and hope you enjoyed. Bye now.